Howdy, we are the 2020 Texas A&M University Robotics team. This video will serve as an overview of the team's rig design, instrumentation, and how we plan to achieve the goal of directional drilling for the 2020 robotics competition. The objective of this year's competition is to drill a well bore to hit multiple targets at varying vertical depths and XY coordinates. We will first go over the mechanical aspects of the rig. This year, the team is going to implement a tensegrity structure to decrease the weight of the structure while not sacrificing the structural integrity. The idea of integrating tensegrity into our drilling rig is considered experimental, and the success of this structure could lead to the implementation of it in the real world. The team has modified the 2019 TAMU drilling rig to be collapsible to be used as a backup if the tensegrity structure were to fail during testing in the spring semester. The previous rig will have 4 45-degree supports as well as 4 L supports screwed into the 2 pillars to provide added support for the drilling rig. The rig will be situated on a 31-inch by 28-inch structure that will allow for the rig to drill the specimen. Furthermore, the structure can be extended to 57 inches to allow for a 24-inch workstation and contracted once again to minimize the size of the structure and improve the mobility of the rig when needed. Wheels will also be attached to the bottom of the forelegs to further improve the mobility of the structure since transportation will be needed for this year's competition. Air will be used as the drilling fluid to evacuate rock shavings from the drilling components to increase drilling efficiency and ROP. The top drive motor is attached to the elevator of the rig that allows for the drill string to move up and down. In order to take on this year's directional drilling competition, we have modified our BHA to include an in-house rotary steerable assembly. The RSS consists of 2 universal joints connected through shafts for power transmission through the drill axis. The assembly contains 4 pistons that when actuated, the steering collar is pushed to the desired configuration and thereby actuating the drill bit itself to the angle required with respect to the drill hole axis. Next, we will be providing an overview of the instrumentation and its use. The goal of the algorithm that the team has constructed is to drill as efficiently as possible while mitigating drilling inconsistencies. This is achieved by minimizing mechanical specific energy. Weight on bit and ROP should be linear, otherwise dysfunctions will arise. MSC will be tracked throughout the drilling process to ensure that there is no whirl or stick slip of the drill string. Weight on bit will be measured using an S-beam load cell to measure tension in the hoisting system. Revolutions per minute will be measured using an optical tachometer. Torque will be measured using an indirect sensor shown on the left and a direct sensor on the right. Depth will be measured from the rig floor as used in last year's competition. Downhole vibrations, inclination, and azimuth will be measured from the sensors located in the BHA. The final topic of this design video will give an overview of the data acquisition and analytics. All data will be collected from each sensor using an electronic drilling recorder based on the National Instrument CDAC and LabVIEW system that will be presented in a user-friendly graphical interface. Real-time drill data will be collected and analyzed using MATLAB and LabVIEW on every control loop based on a reduced order model that is required for mechanical specific energy and the weight on bit ROP correlations. An algorithm that is independent will analyze real-time vibration data to detect bit dysfunctions. Redundancy in the system is achieved using multiple control loops in the system architecture with different loop times varying from 1 to 20,000 Hz. Additionally, a microcontroller schedule-based PID controller will be used to control important drilling parameters such as weight on bit, inclination, and revolutions per minute. It also monitors safety triggers such as temperature, current, and torque limits. A data-based linear quadratic Gaussian control loop will also be used to correct trajectory to achieve our target zone. We get the Markov parameters from the collected data and then use it to perform a new design to minimize a finite horizon LQG problem. We are very excited about this year's competition and to see the design ideas constructed. We would like to thank the organizers, judges, and sponsors for their time and efforts that are put into this competition. Thanks and gig 'em.